Now, Kepler's three laws, the first two do two very important things. Totally destroy these two aesthetics that date back to Aristotle and Plato before him. Circular motion, uniform motion. All the models up to this point, even Copernicus's and Copernicus's corrected model, are making use of circles rotating uniformly. Kepler abandons both of these. With his first law, he abandoned circular motion. So let's read it here. The orbital paths of the planets are elliptical, not circular, with the sun at one focus. Okay, so let's talk about ellipses. Let's get a clean piece of paper here. Okay, so this is Kepler's first law, K1. We're talking about ellipses. So this is how you can make an ellipse. You can go home and make your very own ellipse, very simply. You get a length of string and attach it to whatever with two tacks. Do it such that it's a little loose, and then pull it tight with a pencil. And then as you move the pencil around, keeping it tight, you will get an ellipse. An ellipse is defined as that geometric structure where the distance from the one focus, the one tack, to the pencil and back to the tack is held constant. That gives you an ellipse. So they're easy to make, and there's certain terminology associated with them. You have two axes. You have a long axis we call the major axis. It's the long axis. And you have the minor axis, which is the short axis. And we can define half of the major axis, half of the minor axis. Instead of saying half, we call it semi. So an important quantity that we'll keep referring to is the semi-major axis. Oops. M-A-J-O-R. Semi-major axis. And this is denoted A. Just the lowercase a for axis. But it's referring to the semi-major axis that's half of the long axis. Okay, here we have an ellipse. You see it has two foci. Let me get that term down here. So, focus is the singular, the plural is foci. The ellipse has two foci. It's like it has two centers, if you will. And if I bring those centers closer and closer together until they're on top of each other, what shape am I going to have? A circle. So a circle is a special case of an ellipse. The ellipse is the more general shape. A circle is an ellipse. They're just a special case. Well, the semi-major axis is half of the long axis. If we're talking about the special case of a circle, the semi-major axis is the radius. That's right. So semi-major axis A, it's like the radius R of a circle. So it's analogous. If we're talking about circular orbits and we talk about the distance of the planet from the sun, that's the radius of that circle. Instead, now we're going to be talking about semi-major axes, which is kind of the long radius of the ellipse, if you will. Let's see, one other term, and that's eccentricity. A circle is a circle. But as we move those two foci farther and farther apart, our ellipse becomes more eccentric. So here's a diagram that shows that. So eccentricity 0 is when the two foci are on top of each other. Now these eccentricities, 0.5, 0.9, there's an equation for it. We don't need to know it. Just qualitatively, you can know it goes from 0, which is a circle, all the way up to 1, which is a very elongated ellipse. And the only thing that's changing is the separation of the foci. The equation for the eccentricity is a function of the ratio of the long axis to the short axis. So here we have 0.5 and 0.9 and 0.99. I should say the planets, their eccentricities going around the sun are all very close to 0. And to the point that if I plot the orbit up there, you're going to have a hard time seeing the eccentricity. Maybe you can see it with Mercury and Pluto and some of the other dwarf planets out there. But the big ones tend to be pretty circular. They're not perfectly circular, which is why the ancient models didn't work. But they're pretty close to circular. So you don't have to go up to strong eccentricities like this to describe them. But there are some things that move on those high eccentricity orbits, like comets, for example, they swoop in and swoop out, often with high eccentricity. And what Kepler says in his first law is the orbits are elliptical, but the central mass is at one of the two foci. It's not in the middle, it's at one of the two foci, and the other focus is unoccupied, nothing's there. So you may be wondering, how did Kepler come up with this? And I don't know if anyone really knows, but I have my own private theory that I'm now going to share with you. So he was a Copernican and a mathematician, so I'm sure he spent a lot of time studying Copernicus's model. Not just his original model. Remember, in the original model, he said planets orbit the sun, circular orbits. And it didn't work very well. It worked qualitatively, but quantitatively, it didn't cut it next to Ptolemy. So he tweaked it. He did two things. Drawing from the example of the Ptolemaic model, he offset the center of the orbit from the sun. So here's the orbit. X marks the center, and the sun is shifted. Or you can think of it, the sun is there, and the whole orbit has been shifted. Just like the deferents were shifted in Ptolemy's model, he shifted them as well. Not this extreme amount. It's a small shift, but I just draw it extreme to make it easier to see. The other thing that Copernicus had to add was what? Epicycles. Not big ones, just little ones. So I'm going to draw the epicycle, and the epicycle moves around the orbit just like it moves around the deferent in the Ptolemaic model. I'll draw it in a handful of different positions. And just like in the Ptolemaic model, the planet is attached to the epicycle. Now, Kepler probably knows that the epicycles in the Copernican model all kind of go the same way. The orbits are counterclockwise, the epicycles rotate clockwise. One full rotation per orbit. So I'll draw the planet on here and we'll watch it move about as it goes. So let's start it at this position right here. The epicycle is going around counterclockwise, so it's going to go clockwise. There's an eighth of a rotation, a quarter, 3/8, a half, so forth, and so on, until it's back to its position. They all do this. So Kepler, I think he just looked at this and then connected the dots. So I'm going to connect the dots here. So what does that look like? Looks like an ellipse. Now it's not an ellipse. Technically it's not an ellipse. You can't make an ellipse with two circles in this way. You want to make an ellipse, it has to be as I showed you here. You can't make an ellipse in this way, but you look at it, it's pretty close to an ellipse. Kepler, being a mathematician, said that looks like an ellipse. I wonder if I change the orbits from this strange combination of circles to actual ellipses, would it get better? And in fact, it replicates the observations perfectly. So I think this is how Kepler came up with the idea. And notice, the sun, even though this isn't an ellipse, pretend it's an ellipse. Where would the foci be? Well, looking at this diagram here, what I drew appears to be around 50% eccentric. The foci would be here and here, and that's very close to where the sun is. So he said, okay, the central mass is at one of the two foci, elliptical orbit. And it turned out to be correct. It's really a very simple prescription. It's strange how sometimes we come to truth in very roundabout ways. Now, this is a heliocentric model based on the geocentric model based on an aesthetic of circles and uniformly rotating circles. And it's come, it's like going around the hard way to get to the idea of a simple shape like an ellipse with the sun at one point. This also was made difficult because the orbits of the planets are very close to circular. If they're all extremely elliptical, we might have come to it earlier, because the Ptolemaic model would be even more wrong. The more eccentric you make it, the worse the Ptolemaic model is, and the modified Copernican. Okay, so that's Kepler's first law. Questions there? Y'all like my private theory? Yeah, good. I should publish it. Kepler 2, K2. Okay. This one, the previous one, he destroyed circular motion. Now we're going to destroy uniform motion. What he's talking about is how fast does the planet move as it's going around its orbit. As you'll see in a second, he's basically saying it goes faster when it's close to the central body. A planet goes faster when it's close to the sun, slower when it's farther away. If it's a circular orbit, it's uniform. But if it's an elliptical orbit, sometimes you're closer, sometimes you're farther. He says it's slower the farther you're away, and he specifies it. Now, in the modern day, what we would do is we'd say, at a particular angle, you're going at a particular speed. At a different angle, you're going at a different speed. But maybe mathematics wasn't, configured that way back then. So he writes in this kind of obscure geometric way, but it is correct. An imaginary line connecting the sun to any planet sweeps out equal areas of the ellipse in equal intervals of time. Okay, it's hard to visualize, so let's draw it up here. We've got the sun, and we have an orbit. So a planet's going along this pretty eccentric ellipse. And I should state, the eccentricities of the planets, very small. You can't even see it if you look at the orbits, except maybe for Mercury, maybe for Pluto, and the other dwarf planets out there in the Kuiper Belt. But the big planets beyond Mercury, they're all really close to circular. You wouldn't be able to see it like this. Here is kind of an exaggerated ellipse, just for the sake of understanding it. So when it's far away, it's moving slow. So in the same amount of time, each of these blue areas are filled in over the same amount of time. So in the same amount of time, it only moves a small distance here, far away from the sun. And when you're near the sun, it moves a big distance, because it's going faster close to the sun, slower farther away. How much faster? How much slower? He says, imagine a line connecting the sun to the planet. Now, in a certain amount of time, it's going to sweep out a particular area. That's this whole blue shaded region. Now, since it's moving slow, this is kind of like a triangle. Think of this as a triangle. The base is small, and the other axes are long, because it's far from the sun, small because it's moving slowly. But if you come over here, it's moving faster. So you sweep out more area at the base of your triangle, and this doesn't look like a triangle anymore, but a greater distance on the one side, but you're closer to the sun. So when you kind of multiply those quantities together, you get the same area. This area here, this area C, is exactly the same as this area here. You sweep out equal areas in equal times. That means you're going faster at a particular level when you're close and slower at a particular level when you're far away. Here's the intermediate case. Again, in the same amount of time, you sweep out the same area, which means it has to be going at an intermediate speed, since it's at an intermediate distance. That make sense? It's kind of a strange way of writing it, but that's how Kepler came to it, and that's what he wrote down. Nowadays, we just say that if you're at this angle in the orbit, say that's 0, you're going at a particular speed, and we quantify how fast you go as a function of angle. Here would be the slowest speed, come back around, it would speed up again. It would be some messy equation. So actually, this is kind of an elegant, very short, terse way of describing a complicated motion. But uniform motion is out. He destroys it with the second law. And this brings us to Kepler's third law. And we'll spend some time on this, because you'll see this a lot in this course, various stages in the course. And this is your first real exposure to ratio astronomy. Most of the problems in this course, the homework problems, math problems, are set up as ratios. And I'll explain what that means in a second. It's a different way of wrapping your mind around a problem. Okay, I'll explain what it means now. And since I'm on to it, you're probably most used to plug and chug. For example, take a simple example as distance is speed of light times time, for how far light travels in a certain amount of time. Suppose I give you speed of light in kilometers per second. I give you a certain amount of time in years. Well, I got to convert those years to seconds, multiply it by speed of light in kilometers per second, you get a distance in kilometers, but suppose I'm asking for the distance in light years. Then you got to do another conversion, or something of that nature. Or maybe I'm asking for it in megaparsecs. So you're given something, you got to convert to get it into the right units for your constant of proportionality, and then what you get out, you might have to convert again. Many steps, many possibilities for error. But you can also set all problems up in terms of ratios. If something takes twice as long as something else to travel, it's going to travel twice as far as that something else. And once you wrap your mind around the ratio technique, the mathematics is actually quite easy to do. But it takes a little while to start thinking of things this way. And Kepler's third law will be your first exposure to it. Anyway, let's back up and go to the law, and we'll work it. through an example or two of this ratio approach. The square of a planet's orbital period, p, is proportional to the cube of its semi-major axis, a. So two quantities, p, orbital period, that's the amount of time it takes to do a full orbit, and a is the semi-major axis. It's kind of like the radius if it were a circle, but it's half the major axis of the ellipse. So he's connecting how long it takes a planet to go around the ellipse to how big the ellipse is. So p squared is proportional to a cubed. Proportional. What does that mean? It means p squared is equal to some constant times a cubed. Actually, I'm going to put this up on the next page. We're going to need some space. Let me write that here. P squared is equal to a constant times a cubed. And what he found is that constant's the same for all bodies going around the sun. All the planets, it's the same constant. P squared is equal to that constant times a cubed. Now, we then checked the moons going around Jupiter. They also follow Kepler's third law, but with a different constant. Then you check for the moon going around the Earth. It's just one object, so there's nothing else to compare to, but also follows Kepler's third law, but with a different constant. As you change the central body, you change the constant. Kepler had no idea why. He didn't know why the constants were what they were. It won't be until we get to Newton that that's explained and figured out in physical terms. All that Kepler's doing is empirical work. He's looking at the data, he's coming up with a description for the data. But if you have a central body, you have a constant. Well, suppose I said Jupiter is 5.2 astronomical units away. That would be the problem we'll actually do in a second. You'd have to look at your constant and figure out what the units are, convert your 5.2 astronomical units into those units. You get something out here, and then you're going to have to convert, maybe it comes out in seconds, and I want it in years. That's another conversion. That's a lot of work. So the ratio approach is this. Here's the general equation. Now we're going to take a specific comparison object. Let's take the Earth. Since this only goes for things going around the sun, in fact, I'm going to put a little subscript here. That's the symbol for sun, circle with a dot in it. A circle with a plus sign is Earth, and all the other planets have their own symbols. But here, we're just talking about things going around the sun. So comparison object will be the Earth. Earth goes around the sun with an orbital period of 365 days, or just simply 1 year. So let's write that out here. 1 year squared. In this general case, this special case. 1 year squared is going to be equal to that same constant, all things going around the sun, same constant, times the semi-major axis of Earth's orbit. Now, Earth's orbit's about as circular as it can get, so it's kind of the radius of the orbit, which is the Sun-Earth distance, and we call that 1 astronomical unit. I'll write that on the side in a second. 1 AU is the average Sun-Earth distance. And since Earth's orbit is pretty close to a circle, it's pretty much the semi-major axis of Earth's orbit around the Sun. So here's the general case, here's a specific case just for the Earth. Let's divide these two equations and simplify. On this side, we have p squared over 1 year squared, so we're going to write that as p over 1 year, whole thing squared, quantity squared. The constants cancel out. This is what makes it easy. And then over here, a cubed over 1 AU cubed, we'll write that as a over 1 AU quantity cubed. So now we have an equation that's a little bit easier to use. But again, in the case of Jupiter, it's 5.2 times farther from the sun than the Earth. So it's 5.2 astronomical units. We stick 5.2 astronomical units in here. The AU's cancel, and it's just 5.2 cubed. Take a square root, and you have the period in years. Okay, we'll do this in just a second. Let me write down a couple shorthand ways to remember this. You could write p squared equals a cubed without writing these units here. And this is kind of the shorthand way of writing it. You just have to remember to use consistent units. Use consistent. Is it ENT? ANT. Who cares? Not question, no. Exclamation mark. Use consistent units. If the sun is your central object, years and AUs are consistent units. We can check. Let's consider the case of the Earth. Earth goes around in 1 year, so 1 squared. It says semi-major axis of 1 AU, 1 cubed, question mark. Yes, that's true. So we just checked it for the Earth, and it would be true for anything else going around the Sun as long as we use years and AUs. Now, some of you might not remember fractional exponents. Some of you might. So when you bring your cheat sheets to the exams, you're allowed a cheat sheet. I think I mentioned that before. You might want to have this pre-solved. And the questions will have two forms. I either give you the semi-major axis and ask for the period, or I give you the period and ask for the semi-major axis. We want the period, we take the square root of both sides. That'd be p equals a to the 3/2. If I want the semi-major axis, we take the cube root of both sides. It's a equals p to the 2/3. So these are your two shorthand, pre-solved versions of Kepler's third law. But just remember, use consistent units. If we're talking about something going around the Earth, don't be using years and astronomical units. That only works, this is only true in years and astronomical units for things going around the Sun. If that confuses you, fall back to this equation where the units are written out explicitly. And you can write them in there and cancel them out. Everyone following me so far? Okay, so let's do the case I've been talking about. Jupiter's semi-major axis is equal to 5.2 AU. So if I want the period, the orbital period, the time it takes for Jupiter to go around the Sun, it's this equation. Period is 5.2 to the 3/2, which is, if you plug it into a calculator, 11.9 years. That's simple. If I give you the AU, raise it to the 3/2, and you have the period in years. But you got to remember, and I'll show you, we'll do the case going around the Earth in just a second. You'll see that it's important to use consistent units. If I gave you a period of 11.9 years, you could stick it in here, raise it to the 2/3, and you have 5.2 AU. So you can figure it out for anything going around the Sun. Now, just a little word of caution. When you stick this in your calculator, here's the wrong way to do it. And a lot of people make this mistake, so I'm pointing it out. 5.2 to the 3/2. If you do this, you know what's going to happen, right? Yep, your calculator would do 5.2 to the 3rd, solve that, and divide the whole thing by 2. The correct way is 5.2 to the parenthesis 3/2 unparenthesis, or 5.2 to the 1.5. Just do the 3/2 in your head. So just so you avoid that calculator error, I want to point it out. Okay, let's consider the case of something going around the Earth. Everyone got this? Because I'm out of space here. Same deal. Sometimes it's good to see things twice, and it's going to look very similar. P squared is equal to constant. This time it's a different constant for things going around the Earth. That's the symbol for Earth, times a cubed. Let's take the case of something going around the Earth. The Moon goes around the Earth. The Moon has an orbital period of 1 month. So we'll say I'll just say LM, lunar month, squared equals that same constant for the Earth, times, we'll call it 1 Earth-Moon distance. There's no term like astronomical unit for the distance between the Earth and the Moon. So we'll just say 1 Earth-Moon distance cubed. So this is a general case for things going around Earth. This is a special case. Divide the equations, constants cancel, and we have period measured in lunar months squared is equal to the semi-major axis in Earth-Moon distances cubed. So if I give you a problem with a spacecraft, a satellite in orbit around the Earth, maybe it's in orbit between the Earth and the Moon, maybe it goes out beyond the Moon, and I say its semi-major axis is a certain number of Earth-Moon distances, you just plug that into your p squared equals a cubed. If your unit's Earth-Moon distances, it's going to come out in lunar months. If I give you the period of a spacecraft in lunar months, you solve it for semi-major axis, it comes out in Earth-Moon distances. this is archaeoastronomy. If I give you everything in terms of some other object, the calculation is actually quite simple. It's more about adjusting your mind to doing the mathematics in this way than the plug-and-chug approach where you have to do all the unit conversions. Any questions about that? Yes? Yeah, technically, yeah, right. So, what I mean by Earth-Moon distance here, if I'm going to define it specifically, I'll call that one Earth-Moon semi-major axis. Just to be consistent. I should say you could do this for things going around Jupiter. We have a spacecraft there called Galileo. It's not in use anymore, but it's still out there. If I tell you how long it takes to go around Jupiter in Io months, Io is one of the moons of Jupiter, you could then calculate how far it is from Jupiter Io distances. Just do one example here. Let's take A is equal to P to the 2/3, going around Jupiter. So let's say we talk about Galileo spacecraft going around Jupiter, and I say its period is 2 Io months. Well, how far is it from Jupiter? It's 2 to the 2/3, whatever that is some number measured in Jupiter Io distances. So, as long as everything's in the right units, the mathematics is very simple.